So today we'll finish talking about magnetic particle inspection, looking at uh, kind of the process and some of the things we have to do as part of it. So we were looking at guidelines and where we find the guidelines that we're going to follow while we're performing MPI. And that, for our purposes, from a technician standpoint, those are going to be provided to us typically by the manufacturer and others, or in some other type of technical documentation. So I had this example up. This is out of an engine overhaul manual. And this is one that you'll have in lab when you're performing your tests and that kind of thing. Where we have different size parts, and what type of current direction, or inversely what type of magnetization direction, right? Because the current and the magnetization field direction are 90 degrees to one another. And then the required amperage. Now, for most of these, the amperage, for all of these, actually, they list the same amperage for different ones. So something like crankshaft, where you're doing circular and longitudinal magnetization, you're running 2,000 amps each way. There are some cases where the amperage will be different depending on which way you're running the current through it. And in practice, these are your goal currents, or kind of what you're shooting for. Remember, the idea there is it's strong enough to hopefully to reach that saturation point, or it's strong enough that we want to reach the saturation point without running so much current through the part that we cause it to heat up and get damaged in some manner. And worst case scenario is melting the part, but just as bad. Actually, melting the part, at least you're not going to go put it back in, but probably worst case scenario is a part that's got like hardening or heat treating. You won't know that you damaged the part when you overheat it, but it can actually destroy the heat treating or other processes on it. And so then it also lists things like critical areas, things to look at. Now you're looking at the whole part when you're doing this, but there are definitely things that are to focus on, those areas that are identified as high stress. So like a crankshaft, things like journals, fillets, oil holes. Why would oil holes be important? That's how the oil gets through, so it's important that we have them. Why are they important from an inspection standpoint? What does the oil hole cause? What does any kind of thing like that cause in a part? So the oil hole is going to be a stress riser. It's going to be a weakness. It's going to cause a weakness in the part, and it's going to create a stress riser. So it's an area where if a part is potentially going to crack, that's an area where it probably would propagate from, would be something like that. Same thing with any kind of like 90-degree areas or sharp internal corners, especially. The prop flange here, right? Propeller flange is under a lot of stress. You have a propeller that doesn't want to turn because of air resistance, right? Being forced to turn, and even worse is if it hits something. So if you have a prop strike, you have to perform mag particle on that crankshaft if you want to even think about using it again, for instance. So fatigue cracks, heat cracks if you have a dry journal, or a journal that where it's not getting lubrication properly, it can heat up. Heating can change the properties of the metal. It can make it brittle, and that can result in cracking. And so other things, most of the stuff here we're looking at is fatigue cracking. Piston pins, something called the shear plane area. That's those 2 points where the piston, if we have a vertical cylinder, the piston's being pushed down by the explosive event, and it's pushing against a rod that's pushing up, and so you have those 2 shear planes where that connecting rod's being, or the engine's trying to shear the connecting rod into 3 pieces, or the piston pin into 3 pieces. When we get down to gears, so gears, you can see we have center, conductor, or circular. You can also put so shaft circular, teeth between, heat 2 times at 90 degrees. They're talking about different size gears. And we're looking at things like teeth and splines and keyways in particular. Teeth are high stress areas. You also have a big stress riser at the apex of each of each pair of teeth. There's a V-shaped area, right? That's a huge stress riser area. Same thing with like splines and keyways. Again, there's corners in there. So be aware of that. You can also get radial cracking from the torsion. There's a torsional force being applied to the gear where the gear's being twisted one way and the shaft force is kind of the opposite direction, right? Or you're turning the gear and it's trying to turn a shaft that has some resistance, so the resistance is going to be kind of the opposite. So you get that torsional stressing going on. And so that's where it's important that we run our current two different directions in order to make sure that we try to find any kind of discontinuities or flaws running in whichever direction they may have formed. Let's see. Part of our process also includes a particle concentration check. So this is, remember, the magnetic particle inspection is we have a oil bath, which is known as our carrier solution. And then we have ferromagnetic particles that are coated with some kind of a dye, and most of the time they're coated with a fluorescent material that fluoresces under black light or UV light. And so that, the particles we have to make sure we have enough particles that we're going to be able to see any kind of flaws or discontinuities. At the same time, we don't want so many particles in there. We don't want it so thick with particles that it would obscure those different flaws or discontinuities or things we're looking for. And that's especially if you have parts where you're going to have a lot of non-relevant indication. The higher the concentration, the more particles are going to stick to those non-relevant indication areas, those non-relevant features, and then could hide potentially relevant or real indications that that it's important that we find. And so the oil bath has to be checked regularly, daily at minimum. In a high, an environment where there's a lot of parts being processed throughout the day, you may check it more than once. There might be a check at the beginning of the day, another check at the end of the day to verify that you lost particle concentration. And so the sample, you take a 100 milliliter sample, and the sample is allowed to settle for a minimum of 60 minutes. The longer, the better. Once all the particles have settled, It's not like it's going to overshoot just because you let it sit longer. And then the concentration there should come out to about 0.2 to 0.4 milliliters of particles in a 100 milliliter solution, with 0.3 being the ideal. Okay, and that's the standard for aviation. There may be some other standards out there, and we want to record that particle concentration each time that this is checked. Okay? And so we do that using a centrifuge tube that looks like this. It is a 100 milliliter tube with this little skinny end on the bottom. The skinny end allows us to see the fine particle level. So we fill it to the 100 milliliter mark here at the top. And then down on the skinny end at the bottom, it's going to be graduated. In this case, this one's graduated in 0.1 milliliter increments. Just be careful. We have two different tubes down in our lab. One of them is in 0.1 milliliter increments. The other one has like double increments at 0.05 milliliter increments. So you need to pay attention to what the scale is and which one you're using. So here we've got 1, 2, 3, 4, and 5. So those are 0.1. Our 0.05 would have 10 marks between there, right? Divide that by 10 instead of 5. One thing that will happen, the reason we have to do this is we get an effect called draw out or draw down. And that is every time we test a part, right, we're going to magnetize it and we're going to put these particles on it, and hopefully a lot of the particles stick to it. A certain amount of particles are going to stick to it. At the end, remember, we demagnetize our part, but even though we demagnetize it, it doesn't mean all the particles just fall off of it at that point. And so there's a lot of particles still stuck to it, especially if it's a rough surface part that we're working with. And so then we take the part next door over to a parts washer and clean it off. Now those particles that were stuck to it are no longer in our mag particle bench. They've migrated over and they're in the waste fluid on the parts washer. And so that's where this concentration over time typically drops. There really shouldn't be any reason it goes up unless somebody adds particles. And so it drops over time, and that's why we have to monitor this to make sure that it doesn't drop below that minimum of 0.2. And then when we add it, we have to be careful not to add so many that it overshoots above 0.4. We've had that, if it does overshoot, there's a couple ways. One is you can do like a partial fluid change. You drain some of the fluid out, or you just add additional fluid to reduce the concentration of the particles. The other way is I've got a bunch of magnets down there, and I'll take like a rubber glove and throw the magnets in it, and then run the gloved magnets back and forth in the tank. And that'll cause a ton of especially if the particles have settled to the bottom, I can run them right through the bottom, and a whole bunch of the particles will stick to the glove. And then you just pull the glove out, pull the magnets out, and everything falls in the trash. So there's ways to do it, but adjustment is it's a kind of a, when you first set it up, if you know how much fluid you're putting in, you can kind of calculate how many, teaspoons of particles you put in and whatnot. But ultimately, most of the time adjusting it is just kind of, you get a feel for, well, if it's this low, how many, whatever little scoop I have for my particles, how much do I put in? And then you have to take a sample. Once you've added it, you have to take a sample. You have to let it mix up for a little while. Then you have to take your sample, and then it's got to sit again for an hour. And so the process of getting it dialed in can sometimes take a little bit of time, just because there is no quick way unless you have an active centrifuge. So these are passive centrifuge tubes. They just sit there and use gravity. There are ways to do this. If you have an active centrifuge that can actually spin the tubes, you can make it happen a lot faster. Really, the only organizations that would have that is somewhere, again, that's doing this all the time and doing it fast. Everyone knows the term squirrel? Should I say snowplow? Okay. Our bench is an AC, alternating current mag particle bench. It runs alternating current through our parts. There are benches that can do DC. So the most benches are AC only. You can get specialty equipment that has DC. The reason we would use DC is a DC current can result in a deeper penetration of magnetism. That means with an AC system, most of your magnetism forms around the outer layer of the part, which is good for finding like surface cracks or near surface cracks. If you're looking for subsurface defects, then DC causes that magnetic field to form deeper in the part. And so it can be used to find a little bit deeper flaws. And so, again, most equipment is AC, but here's a magnetic field strength profile for DC current. So you can see if we look from the core of the part, the center of the part, moving out to the edge, you can see it's still strongest. Our field's still strongest at the surface, but we have a pretty linear increase as we go from the center of the part out to the surface, right? And then as you move away from the part, right, we can still detect magnetic field, but it drops off, and this is it drops off logarithmically at that point. Here is what AC looks like. So you can see it's got a logarithmic buildup as well instead of linear. So most of that field strength is near the surface. If I put them side by side with AC on the left and DC on the right, you can see again, there's still the majority of the field is near the surface, but this is where we have the ability to see or detect internal flaws a little bit better using a DC bench, if that's what we're doing. So we had this when I worked at the factory where we did forging. We had a DC bench because when you forge parts, sometimes you get metal that folds over itself, and it causes what are called laps inside of it. You can't see it. Once the metal forms, it pushes the surface together, but there might be a gap or a fold inside. And so they had a DC bench to be able to look for that internal to the part in order to kind of see that. But for our purposes, most aviation stuff is going to be run on an AC bench. Kind of the last step after we've done our inspections is that demagnetizing, or second to last step if you want to count cleaning. But here, when we are going to demagnetize the part, we need to return the magnetic field essentially to zero. And earlier in the lecture, we talked about the reasons for that. We don't want our magnetized part being put back on an airplane and causing issues with radio communication or navigation instruments. We don't want a magnetized part being put back into an engine, whether it be turbine or recip, and being a spot where metal shavings want to collect and stick. We'd rather those get flushed around in the oil, go to the oil filter, and so that we don't have a bunch of metal shavings, say, getting caught in a bearing journal or something like that, where it's going to grind the part apart. And so we need to actively demagnetize our part once we're done with it. So what we're going to do is our part, again, we're going to place it in an AC coil where the magnetic field is present to begin with. But then we are going to, that part is going to be subject to a decreasing magnetic field, or what's known as a collapsing magnetic field. And there's two ways that you can do this. So the first would be, most people think about, okay, we turn the magnetizing current down, right? Well, when we're in lab, when I do the demo, one of the things I tell the groups is, do not adjust the current while the bench is operating. It's running a high voltage. If you try to turn that knob or dial, it will arc the control knob and it'll damage it. So it's not designed to have the current adjusted while the bench is actually sending current through the part. So the other option for that is, we can move the part away from or out of that magnetic field. And that's what we're going to do, is physically take the part. We're going to start with it. We're going to use the coil. We will we'll hold the part in the coil, not clamp it into the head and tail stock, but simply just hold it there. And then press, set the power setting to somewhere about mid-range, 5 or 6. Press and hold the button that runs, and make sure our bench is set to coil, send the current through the coil. And then press and hold the button that runs that current. And as we're doing that, we're going to take our part and draw it out physically away from the coil. And then we're going to shut the bench. We're going to release the button that turns it on, put that part back in, turn it on again. And it helps to kind of turn the part in different orientations as you're doing this. And you'll do that 2 or 3 times. If you have a large part, like a crankshaft, you may have to do one end of it a couple times. You may have to do then flip it around and do the other end a couple times. The bigger the part, the harder it is to fully demagnetize it, the more passes it takes. And again, a big part may be a 2-person job. You may, a crankshaft weighing 40, 50, 60 pounds, that may be somebody holding it and doing the drawing out, while a second person is activating the current through the coil. And the reason that works is, we'll go back, here is our hysteresis curve. How many of you have seen Mike's memes in his office in the tool room? This might be getting into why I have the meme that I do up there. But anyways, the hysteresis curve. So earlier I showed you one kind of loop of this, right? This outermost loop. And so what's happening is, remember, we have our field strength is B, or sorry, the residual magnetism, the level of magnetism the part's exhibiting is B. H is the magnetizing force. And so what's happening is, if we just shut the current off, remember, that's going to return back to a retentivity point. So, we started up here, positive B. We turn our current on, right? If we just turned it off, it would stay, either positive or negative B, 1 block down from it. But as we draw our part away, each time it's going to get further and further. It's not going to quite reach. Each time that field flips back and forth, it's not going to get back to that saturation point as you pull the part further and further and further away from that magnetizing field that we're creating with the coil. And so as it does that, you can see the flux density gets closer and closer to the x-axis, to 0. To the point where, as that drops essentially to 0, once we get the part far enough away, as we move from experiencing some kind of magnetism to away, right, that will bring the flux density that's present in the part back to 0. Essentially, it's scrambling, re-scrambling all those individual poles for the different, atoms or molecules in the part. And so we bring it back to that non-magnetic state. And once we've done that, then, just like when we magnetized the part and we made sure that there was a magnetic field present before we performed our inspection, we need to grab our Gauss gauge again and we need to check the part and make sure that there is no residual magnetism in the part at that point. Make sure it doesn't read anything on the Gauss gauge. Okay? And then you can take your part next door or to wherever your parts washing equipment is, and clean off the residual fluid and particles that may still be stuck to the part before putting it back in, if it's serviceable, or sending it out to be recycled or whatever if it's not. So.